Okay. Okay, welcome to the Friday afternoon seminar. So this is actually our third proud alumni speaker of this quarter's series. We actually have quite a few of them. So today we're glad to have Professor Jane Lin from University of Illinois, Chicago. As I mentioned, she graduated from here a while back.
Many years ago.
So she's an associate professor in the Civil and Environmental Engineering Department, and also with the Institute for Environmental Science and Policy at Illinois, Chicago. She has been very active serving on the Transportation Research Board, was the past chair of the Committee on
Transportation
and Air Quality, right? And also associate editor for a few transportation-related journals, including Transportation Research Part D. Her research focuses on air quality, grain freight and urban logistics, and also computational transportation science. So let's welcome Jane.
Thank you. Thanks. So yeah, so it's always great to come back to Davis. So I had a great time when I was a student here at Davis. So I hope you do too. It's a great place, and I took a walk this morning on campus, and it's just like when I was a student, I did appreciate the time I had here and the education I received at Davis. But now this morning when I was walking on campus, I feel a lot more appreciation for the nice campus environment at Davis. So you guys are very lucky. Thank you so much for inviting me to give a talk. Just before I start my talk, I want to show hands, like how many are engineering students and how many are TTP students and everything else.
So first engineering?
Civil engineering,
or industrial engineering, whatever.
Yeah. Okay.
And TTP students. Okay, and what about the others?
Community development.
Oh, okay. All right, great. Okay, so yeah, my talk is not much technical because given the diversity of the audience, so hopefully I achieved that. So the focus of my talk is on the last mile logistics. And so with the focus on the operation efficiency, the energy consumption and emissions, environmental impact. So I will explain what last mile logistics as I go along. So just some very well-known statistics between freight and environment. So we know that transportation contributes about 2/3 of the petroleum-based fuel use, and also contribute like over 1/3 of the carbon emissions and other harmful pollutants, right? And specifically in freight, so freight, even though in terms of the number of vehicles, like if you're looking at the surface transportation, so freight is very small portion of the total traffic, but freight sector actually accounts for over a quarter of the total energy consumption and emissions. And the most important thing is the freight sector is the fastest growing source of transportation emissions globally. And in fact, if you look at the freight, if you look at like the trucking in freight is growing much faster compared to the rail mode in freight, right? So in fact, if you look at the distribution of the tonnage by mode in freight, this is a little bit old data, 2015. So you see that this part is the trucking part of it. So the total trucking is about 70% of all the tonnage moved in the US. And so just a little bit, TL stands for the truckload, which is, you can think of it as this large direct shipment of goods. And the LTL stands for the less than truckload. So these are more like the short distance, think of it as the urban delivery trucks. And the private is not for hire. So for example, Walmart has its own fleet, logistics fleet, Target has its own, so these are the private ones. So all this combined, so trucking accounts for 70% of the total tonnage in the US. And so if we look specifically into the trucking industry, so one of the interesting features of this the trucking industry is it's very highly fragmented in trucking industry. What that means is, if you look at, this is just the same we saw previously, but just focus on the trucking industry. So you have about half a private trucking fleet and the for-hire truckload fleet. But the interesting thing is the large carriers only account for 3% of the total fleet in the trucking industry, and the rest of the 97% are the small, like family-owned, one truck kind of trucking business. So and the top 20 for hire truckload carriers only account for 11% of the total trucking movements. So that's a very interesting nature of the trucking industry, and also it makes it very, very challenging problem and very, very difficult to really solve the problems associated with the trucking industry. And so this slide shows what last mile logistics I'm focusing on in this talk. So if you look at the entire supply chain logistics, so basically you have from the manufacturer or the producer side all the way to the end user, right? So roughly speaking, you can divide the logistics into these three stages. So this from the manufacturers to the distribution centers, the regional distribution centers or the warehouses. So this part typically is associated with the long haul trucking. Okay, and then from the distribution centers to like the retailers or another smaller local urban hubs, this is considered a short haul trucking movement. And then anything from like the retailers or the local hubs to the end users. So sort of the last mile movement, that's the last mile logistics. And so this is really the focus of my talk today. Okay, so why are we interested in the last mile logistics? So it turns out that this is the most challenging problem in the entire logistics, because as you can imagine, for the long haul portion and even the short haul portion, so the dispatching, the scheduling, the routing of trucks are relatively straightforward, right? So you use the highway system to move the truck from the manufacturers to the DCs, so that's relatively straightforward. You don't have a lot of options to move the goods. However, if you look at the last mile especially in the urban environment, so you have a lot of modes you can choose from, right? And also a lot of other factors at work, like you have to fight the local traffic, congestions and all these things. And also, especially with the fast-growing e-commerce, so this has become, the last mile becomes a really, really challenging problem. And unfortunately, this also makes it the least efficient portion of the entire logistics, So that's why it's a very interesting problem to work on, but it's also very challenging. So typically, when you think of the last mile delivery strategies, you want to achieve these 3 Ps or the triple P, right? So you have to think of the people, you want to serve the customers, right? And you also want to be environmentally friendly as well as making money, right? So these are the 3 Ps. Typically, when the logistics company are running their business, they have to keep those things in mind. In my talk, so in the abstract I sent to Anne-Marie, so I mentioned that I'm going to talk about 4 trends, major trends that I consider that are happening in the last mile logistics. They are electrification, the emergence of crowd shipping or crowdsourcing, and the expedited delivery service, and urban consolidated logistics service. So unfortunately, I think I was being overly ambitious. And so I don't think I have time to go over all 4 of them. So in today's talk, I'm going to just focus the first 2, highlighted in red. So I'm going to focus a lot more in detail in the electrification and crowd shipping. And by the way, so I don't mind not finishing my talk at all, the slides at all, but I really want to be interactive. So feel free to stop me if you have any questions or you think I'm wrong, and we can have a talk about like why you think I'm wrong and why I think I'm right. Yes.
I have a quick question. I see that you have separated the same day or like expedited delivery service from the crowdsourcing. Do you mean that it's not possible?
Yes, very good observation. So these 2 are oftentimes linked, right? So especially nowadays for like FedEx or UPS to really apply provide this expedited service like 1 day or 1 hour service like Amazon Prime Now. So they really have to rely on crowd shipping. So these are very much related, but I will talk about, so there is some differences between the 2. I'll touch on that, but very good question. Keep that in mind. So for the other 2 trends, you can refer to some of my publications on that. Okay. So the first trend, electrification. So I don't think I really need to say much about electrification. So California is like the place for electrification research, right? So this is some pictures showing, this is the e-highway concept proposed by Siemens. And I think this picture was actually taken in Sweden. So they had a demo, pilot project, like I think a mile long or something, for this e-highway system. Basically allows the trucks to continuous charge in real time. And this is just the Tesla, the semi-truck that they I think they've been working on this for a few years now. So it's supposed to be a really like a fast and high-end freight truck, right? So in this talk, so my focus is really on the battery electric truck. So I'm not talking about the hybrid, the plug-in electric truck, but the battery electric truck in last mile delivery. So if you're familiar with this topic, so you look at the literature. So most of the literature focus on the life cycle cost of battery electric trucks, especially the battery cost, right? The battery life cost. So not so much focus on the operation side of it, like when you use the truck for last mile delivery, what is the operation cost? But nonetheless, the literature generally agrees about trucks. The BETs are obviously using less energy, more environmental friendly, but they are more expensive to own and operate. So that's the general finding in the literature. Okay, so then we say, well, okay, then we really want to find out the answers to all these questions. Okay, so specifically looking at the BETs in the last mile delivery. So how does the network affect the operation? Okay, so is there like a right network size for BETs? So and the customer density or the number of customers, how does it scale it up? And the battery capacity. So is there a right battery capacity in terms of the operating cost, right? So is it maybe too big, it's not good, or too small, it's not good. So is there a right battery size? And what about the number of charging stations? Do they matter? So we know that nowadays people are talking about building more charging stations, we need more charging stations. Is that really the case in the last mile delivery? And what about the vehicle capacity, like the size of the vehicle? So should we have a bigger size BET, so should we have a smaller size BET? How does that affect the daily operation in the last mile delivery? And what about the charging, the charging technology? Is it faster charging better or slower charging better? So these are the questions we're trying to find out the answers for. Okay. So to do that first, in this study that we conducted, so we first introduced this concept of daily operating cost of BET. So here, really, the operating costs, we only consider 3 components of this daily operating costs. So one is the driver's wage. Okay, so we have to hire the drivers to go around and deliver goods, right? And then also in this study, we allow the trucks to stop and recharge the battery. So in practice, a lot of the carriers actually do not allow trucks, the BETs, to actually stop and recharge, because consider that's idling time. You know, it costs money to do that. But just hypothetically, we say, well, let's say we allow that. Okay, what would happen? Obviously, if it turns out to be non-economical, obviously you can, you know, they don't have to go charge, right? So, but we don't limit that. We say, okay, we consider that, well, the drivers can stop and recharge their battery en route to their delivery. So, but you have to take that into account, because the drivers are still working, so that you have to pay the drivers for the time they're waiting for the battery to be recharged. And also, we also consider the energy cost. So the electricity cost associated with the battery use, right? And so essentially, so this is the only formula I have for my talk. So bear with me. So basically, the idea is, well, we're trying to minimize this total daily operating cost. Okay, the 3 components, right? The driver wage and then the energy consumption, right? Subject to a number of constraints. Okay. So then we also look at other performance to see, well, okay, there may be trade-offs. You know, besides the operating cost. So we look at, well, the level of service, number of customers served, the number of BETs dispatched, basically the fleet size, and the total VMT. We also look at the per mile, the recharging time, the per mile energy use, and the per mile daily operating cost. Okay. So the way we did it is, you know, this is a completely hypothetical. Okay, so we consider a hypothetical network. So it's basically a square, a service area, and then we have the customers randomly, uniformly distributed within the service area, and then assuming there's only one depot for all the trucks to go back and forth, and then the base case we consider only one charging station at the center of the area, and then we consider a number of key factors in this investigation. So we say, well, we vary the network size. Say this is 25 mile by 25 mile, 50 by 50, and 100 by 100. So just give you the perspective. 25 by 25 mile is about the size of city of Chicago. Okay, within the city limit. Okay, so in other words, this sort of represents the urban scale. And the 50 by 50 is about the Cook County, which is where city of Chicago located. So that's kind of like the county scale, and 100 by 100 is the metropolitan region of Chicago. So that's like the regional scale. Yes.
I'm interested in the network size that a milk truck would have handled when I was a boy. Mm-hmm. And it could be a horse-drawn mm-hmm. vehicle. So, and the reason I'm asking this is an electric assist bicycle, which has a large capacity. It could handle half a ton with no problem with the proper design. So, could you address that scale as well?
So I didn't consider the electric bicycles, but if you consider the vehicles, you know, with the similar capacity, so that we can look at this as also the electric bicycles. So what is the network scale you're
I think it would be five miles.
Oh, 5 miles
or 10 miles.
Okay, so we could certainly go down to that level. Yeah. So we can vary this, but we just pick this three because it's about the urban logistics. Yeah, but yeah, definitely it doesn't. Definitely the model can handle that. Yeah. Yes.
I have a question about the network. So when you say network, you mean the
service
area
size, the service area.
in terms of Euclidean distance, or the distance is measured by travel time?
Oh, it's just the distance.
It's a network.
Yeah, it's just the distance. Like this will be 25 by 25.
Basically like greater.
Yeah,
area.
yeah. So I just assume a simple square
So,
area.
No congestion considered. in this case.
Well, so we assume like average speed. So yeah, on the next slide I'll show you that. But you can certainly vary that speed to see the effect of that. Yeah. So yeah. So and then we obviously I consider the battery capacity for BETs. So 50 kilowatt hours all the way to 150. So the three scenarios. And the charging stations I consider symmetrically distributed, so 1, 2, 4, 5, all the way to 16. And number of customers I consider lowercase 30 versus a higher case 100. But obviously you can also go scale it up to more. And the vehicle capacity I consider this three cases, and the charging rate I consider 15 kilowatt charging rate, so which is kind of like the level 2. Currently, and all the way to 300 kilowatt charging rate. Okay, so we consider a total of 43 scenarios. So the first set of scenario we consider joint effect of the network size, battery capacity, and the number of customers. And the second set of the scenarios we consider the joint effect of number of charging stations and number of customers. And the third set, we consider the joint effect of vehicle capacity and number of customers. And the last set, we consider joint effect of the charging rate and the number of customers. So we consider both low customer density and high customer density in all the cases. Okay, so these are some of the other model parameters, just to highlight a couple of them. So we consider, for example, the hourly driver wage. Probably this is now a little bit low end because we did this some time ago. The battery cost is 12 cents per kilowatt hour. Okay, so the first set of scenarios. Okay, we consider the joint effect of network size and battery capacity by number of customers. So this table shows the 30 customers, and this table shows the 100 customers. And so this is just a scenario ID, okay? And this is the network size, and the number in the parentheses is the battery capacity. And this is the number of customers served, number of BETs dispatched, and the total VMT. And the value in the parentheses is the standard deviation of that total VMT. So one thing you see right away is, you know, in some cases, especially when you have high customer density, not all the customers are served. You have a question? Yes.
Yeah. Are you doing any sort of like route inspection optimization?
Yeah.
Okay. Is that dependent on the inputs that you're putting in, like battery, like time to charge, or like battery size?
Of course. Yeah.
Okay,
Yeah. So in this case, you know, if you go back to the previous slide, so these are the variable, the parameters, I assume.
Okay. So it's just not going, and then it has to go to charge.
So in the model, we allow the drivers to charge when they are in route to do the delivery. So if they decide that, well, the battery is too low, I cannot deliver the package to the next customer, then the driver will visit the charging station.
Okay.
To recharge. Yeah. Okay. So essentially, yeah. So the key thing here is that, well, it turns out there is a feasible network size. So it depends on a lot of things, specifically the capacity, battery capacity, and number of customers, or the customer density. So in this experiment, I wouldn't say that I don't want to generalize this, but we find out that in this case, so this, if you look at this blog, So this represents, I mentioned, represents the regional network size. So it turns out that the BET is not feasible to serve the regional size, even when we actually increase the battery capacity to 300 kilowatt hours, which is right now not very common in the marketplace for BETs. So with this large battery size, still it cannot serve the regional, the regional scale. So then in the rest of the analysis, we just focus on.
Question.
Yes.
So how do you decide it's not good? Are you benchmarking with the ICs or?
So yeah. So good question. So when we say, well, whether the service is feasible or not, so we just based on this one. So if you cannot serve all the customers, then obviously it's not feasible.
Is it percentage or the?
No, this is the total number of customers, because the total number is 100. So you need to serve all 100 customers. If you cannot serve all 100 customers, you don't deliver your service, right? So basically, when we say a feasible service network, we just simply define that as, you're serving all the customers.
So you obviously have some constraints on the service quality. Otherwise, because they can charge, so they can always serve them.
So yeah, okay. Good question. Good question. So we don't limit the number of BETs you can dispatch. The model will decide how many BETs will dispatch. But no matter what, so we try, because we just randomly generate 50 different instances for each case and see how and then you route the BETs, and they're not able to serve 100 customers.
In 10 hours or 8 hours? Is that
the whole day. Yeah,
24 hours.
It's 8 hours.
8 hours.
But we don't limit the number of BETs you can dispatch. But of course, you can always dispatch a direct, vehicle, non-BET, to serve the customers. But we assume all the vehicles are BETs.
Right. So why not each customer has a BET, and with charging, so they can be served.
Well,
But-
no, because even with this battery capacity, it's out of range. It's out of range with this network size.
With the charging of just one charging.
Right.
Okay. So
Yeah.
that's the problem.
Well, but later on I'll show even with more charging station, it doesn't help. Yeah. Why?
we'll see.
We'll talk about it. Yeah.
Basically, so for instance, the scenario 15,
Uh-huh.
you have only 100. It means that in all the cases that you did, all the runs that you had, you can always serve all the customers.
So yeah. So we did 50
Yeah.
runs for each one.
If
Yeah, so
all
for
of them
all so if you see this range, it means that some
Yeah.
have only served 64,
Yeah.
some only serve up to 73, and then in between. So this is the lower bound and this is the upper bound. But in this case, it served all the customers. And in the case of the 30 customers, except for this one, all of them are served.
so you can assume it's a bit. You have more capacity than needed if you always are able to
Right,
serve.
right, yeah. So absolutely, yeah. Yes.
How is the location of the customers? How is that simulated? How did you?
Just
do that?
randomly generated, uniformly
And
distributed.
does that change? So the dispersion of that would.
Every instance we run, we randomly generate the customer's location. Yeah, we don't fix the customer. Yes.
But how's the performance? This is scenarios if you compare with regular vehicles, for example, diesel or gasoline vehicles. So is that a fair comparison?
So for these conventional vehicles, I think they can always serve a lot of customers.
So
Right.
but I don't understand this. Why is the biggest constraint? Why they are not able to do it? Is it because the battery lifetime? Was it because another constraint?
I think it's the combination of the network, the service area, and the battery capacity. So we didn't try like even bigger battery capacity, because right now it's just unrealistic, right? So because even 300 kilowatt hour is considered it's not currently in the market yet. So, but if you increase this, so the solution maybe, well, it could serve 100, all 100 customers. But the thing is, if you look at this one and this one, so with a smaller network size or the service area, so it did achieve all the customers.
But you mentioned that the number of the BETs is unlimited.
So we don't have a cap. So this is determined by the model. So how many BETs are needed for doing the job. So this is as much as you can get, keeping in mind that you want to minimize your cost. But we don't consider the capital investment of buying the BETs.
So I think the key here is every successful one has a standard deviation of total BMTs of under 100, with the number 9 being 63. All the unsuccessful ones are over 100 standard deviation.
I don't think that's really the main reason for it. You're talking about this one here?
Oh, number 9 is the 63.
This
There's
one.
a 62 at 15, but all the unsuccessful ones are over 100, so they're just outside the.
Oh, but this is a different case. This is a number of customers 30, and that's so the network size is much larger.
It's the case in every one.
So, well, it seems like that's to be the case, but that's what she said. That's not the reason. It's an effect of somehow
Right.
coincide with that.
It's larger.
Right. Yes, you have a question.
So you try to maximize the number of customers served in all the scenarios.
No, we don't. The
So
objective function is just to minimize cost. Yeah.
Total
The
cost.
number
But you have to serve all the customers. Well, so we let the model decide on how many customers it can serve
Okay, so
With
that's
minimum
why
cost.
you didn't dispatch.
within 8 hour operating time.
That's why you didn't dispatch 100 BETs to serve 100 customers.
Right.
Yeah,
Right.
that's the first way
Right. So
to
you say
serve 100 people,
direct
yeah.
shipment, but even with that, sometimes because of the range, you may not be able to. Well, yeah, I guess in that case, you can always go to the charging station and then go on. Yeah.
So
you're saying-
yes, the question is, so the daily operating cost doesn't really impact the total number of customers served, right? I mean, you minimize the total operating cost or not, it still cannot serve all the customers in, for example, other.
Right. Yeah. So so it shouldn't affect the number of customers served. So this is the number of customers served is a result of the network, the service area, and the battery capacity. So because essentially what this says is that there is a certain range that the BET can serve. So beyond that, the simply just by increasing the fleet size, you won't be able to serve.
So put it the other way, is I can put a constraint on the customer not served, give a high cost. Okay, so I'll penalize if you don't serve a customer. I'll penalize the.
Sure. Yeah.
And then would you, like in some cases, you get an infeasible solution. It seems like that's what.
Yes. Yeah. If we're trying to do that, then we won't be able to get a solution.
So does that mean that if you don't care about costs, then you can, right? I mean, the
Sure,
limiting
sure.
factor is the cost here.
Right.
So yeah, I guess that's.
Which means that you, I mean, instead of put a constraint, you could also maximize the revenues, basically. But the difference between the revenues and the cost, because of course, if you don't serve customers, means that there are missed revenues there.
Right. Yeah. You can either put it as a constraint or yeah.
But what would be the cost of serving all the customers in each case? I mean, do you have a relationship? between
No,
cost
yeah,
and-
we didn't quantify that. But
That's
obviously,
obvious.
we could include that into the objective, right? So because obviously this is a big deal for any business, right? You don't serve your customers, and you don't have your business.
I think from the perspective of policy making, for example, you would like to know how much more it would cost, and you will have to provide as incentives, for example, in order to be able to use.
Right. Yeah. We didn't consider that in this, but that's a very good point. Yeah. Yes.
So in this particular scenario, what's the charging rate considered when you?
For this particular one, we assume 15 kilowatt. Yeah.
Okay.
Yeah, but as you can see on the next slide, which I'm just so even the charging time is very small. So this is in minutes per mile. So the charging time is really doesn't really affect anything, because what happens is the carriers will work out a strategy to minimize that recharging time anyway, because it's not the time that matters, it's the cost you pay the drivers. You know, they don't want that to be too much, right? So, but if you look at the energy use, so essentially, you know, if you compare the blue bar and the orange bar, so when you have a lower customer density, it always has higher energy consumption, which makes sense. But both when the battery size goes up, so the energy use and the in-route charging time increases. So this is for another finding. And if you look at the average daily operating cost, so again, the average operating cost when the customer density is higher, then it's lower, which is this orange bar. And if the customer density is lower, then the cost is higher. So also you see that when the customer density is lower, so actually the cost increases as the battery size increases. And actually at an accelerating rate also. But when you look at when the customer density is high, which is the number of customers is high, so the difference is very small. It's almost constant cost, daily cost. Okay, and we also check that it's in the ballpark very similar to the current operating costs of conventional trucks. But nonetheless, so we do see this economy of scale. So as the customer density goes up, so it becomes more cost efficient. So that's good news for BET.
In this case, what was the average speed you assume?
Oh, we assume 30 miles per hour.
30 miles per hour.
So the second one, we consider the charging station. So previous scenario, we only consider one in the center of the service area. So in this case, we consider these 5 different scenarios, and keeping everything else the same. So what we see here is that when you increase the charging station, whether you look at the number of the BETs, customer served, VMT, all these performance measures, they don't matter. So the number of charging stations actually does not affect the daily operation, which is a very interesting finding in the study, because obviously I think if you look at the literature, most of them will say, well, we need more charging stations, let's build charging stations. But what we find out is that actually you look at them, they're very, very consistent. They don't change that much.
Question.
Yes.
So you mean all these experiments, they all serve the 100 customers, right?
Well, so the upper block is the 100 customers, the lower one is 30.
So they all meet the target, right?
Yes. So you see that they all serve.
So the difference with the previous run is that now they stop to charge. Before they weren't.
No, they all allowed to stop and charge. The previous one only assumed one charging station, and this scenario considers different number of charging stations.
I think what the JP is trying to say is now the number of customers served change all to 100. In the previous one that you showed,
That's
they were not
50 miles.
Yeah. So I forgot to mention that so in the rest of the scenario, we only consider this one. The network size is set at 50 by 50 miles per hour, square miles, and the battery capacity is 150. Yeah. So to guarantee that all customers are served.
So that could be different once you get to the regional scale, right? The results could be different when you get to the regional scale.
Well, but then you don't serve all the customers.
Well, if you have more charging stations, you could have served all the customers.
That's possible, but that's not what that scenario is about. We assume all the customers. Well, so we limit that so that all the customers are served, and then we want to look at if the charging stations will make a difference. Number of charging stations.
The case is, yeah, I was saying that in the bigger scale, a lot of customers.
We could like look at that again and see if all the customers will be served. Right? Yeah.
So basically, this is a graded algorithm, right? You go one step by one step. This optimization, you just go step by step, not like overall optimization.
This is just sensitivity analysis. We run all these different scenarios.
But I mean, like if you set two target, the total cost, also like you set the number of customers you couldn't serve, it's two target as two like optimizing target, or you combine them together. I think they're gonna be a different optimization problem, right?
Right. So if you're, you can have this bi-level, just talking about the bi-level optimization, you know, optimize the number of customers. But here we said that these are the number of customers you have to serve. No matter what, you have to serve them. That's basically what we're saying. Yes.
So the fact that the number of charging stations has no effect,
right?
What does that mean? That they don't need to charge?
So yeah, actually, I'd like to have a discussion. Why? So what I think. So first of all, I have to mention that there is a caveat in the model, which is we assume unlimited capacity at the charging station. There's no limit how many trucks can go and charge at the same time, right? But I do think that that's what the so basically we assume that there's sufficient number of charging stations or slots you can use. But that's really basically reflect what's now. So because we don't have, I mean, maybe not so much in California, but in say Chicago, we don't have a lot of the EVs. So I think we do have sufficient charging facilities to do that. So what I really think happening is a behavioral adaptation, or a strategic adaptation. So keep in mind, these are not for passengers. These are commercial vehicles. So for the carriers, in order to optimize the operation, so they basically don't prefer the EVs or the BETs to go and charge if they don't have to. They want them to charge as little as possible during their daily operation. Okay, so if they could just, so one thing I should mention also, we allow partial charging in the model. So you don't have to always charge to full capacity. So you can charge just a little bit to get you going. So in that case, you don't have to always wait there for 1 hour for the battery to charge. Yes.
Are you calling out, like, I don't know, maybe you could call it like deadheading for like the BETs to go charge because they're not doing what their job is when they have to go charge code. So I'm interested if there's like a lot of EMT where they're just trying to go charge, and in the different cases.
So we consider that cost in the total daily operating cost, right? So if the driver has to go charge, so that the time the driver drives to the charging station, as well as the time the driver has to wait for the battery to be charged, that's cost. So we consider that cost in the total daily operating cost. Does that kind of answer your question?
Well, yeah, I mean, it's unintuitive that the number of charging stations don't make a difference, because I'd say, oh, if you have 4 charging stations, you're going to be right next to one whenever you need it, so that deadheading time goes down.
So I think in this case, because it seems like just one charging station is sufficiently to do the job, so adding more doesn't seem to make a difference. So
I think that's the key.
Yeah. So this could be an artificial, fact that because the network setting that one charging station is sufficient to do the job. So adding more doesn't make a difference because the carriers are not going to change their strategy to say, well, don't charge now, because you have one more charging station.
Yeah, so I think that's the key because you basically were saying, okay, if I don't charge, I can cover the whole area.
Right.
And then you have an additional cost for charging, so your optimization
Exactly.
will do away. But that's because you constrain the box of their
Right.
assumption.
Right.
But if the
so if I consider like a different setting,
right,
that could be different. Yes. So I'm not trying to generalize findings here, but I think that this is because one, for this setting is sufficient. No, they don't have to go do more charging when you have more stations available. Does that make sense?
I have a question. I was thinking like real cases, not so much as a model, but if each vehicle works for 8 hours at 30 miles per hour, and most it does 240. And then if the capacity is 150, it only really needs to charge once. If all the vehicles belong to the same company, I mean, these are private stations, not public stations. Then are they synchronizing in a way, like, they take turns at charging, so therefore there's less needs for stations or something?
No, so as I mentioned, so I assume there's sufficient capacity, so they can charge simultaneously. You don't have to take turn. So that's a caveat of this. We didn't give a constraint to the model to say that, well, for each station you only have like 2 slots or 5 slots. So at most you have 5 trucks to charge at the same time.
And also you're not limiting the fleet size. Basically, you got an infinite supply of BETs.
Exactly. Yes.
But each BET has a capacity, right?
Right.
So what's the carrier's behavior assumption? Do they go pick as many as they can and form a tour and then go back to the depot and then come out?
Yeah.
And so you have to deal with the multiple vehicle routing problem,
Yes.
optimization problem.
Yeah. So it's a VRT problem.
Yeah. And a multiple.
Yes.
Single depot,
Very
multiple.
hard to solve.
Right. Yeah. Yes.
Is the number of BETs not constrained in all scenarios?
Right. So this is a model result. We don't constrain the. I mean, we can give a very high upper bound,
I think, do you think we should consider the depreciation cost in our daily operating cost? I mean, maybe we should have a large number of BETs to meet the customers. So maybe we should consider we should consider the maintenance and the depreciation cost.
Absolutely. So one of the criticisms we got when we submitted this paper was that you don't consider the purchase cost, right? That's a big deal because BETs are more expensive than conventional trucks. So our response was that, well, because we deliberately not consider that because we only consider operating, daily operating. So we don't look at the capital investment at the beginning, when you purchase this, and then you can factor into per mile cost. So that's sort of by design, But I absolutely agree with you. If you have to consider like the maintenance and repair and all these things, so picture will be very different. Yes.
Just one comment. Yeah, I think maybe it's even more interesting if you could look from like a fleet operator to consider a total cost ownership analysis. Like consider fleet maybe using this kind of fixed fleet to like serve this like number of customers.
Yeah.
TCO. I mean just TCO.
Sure. Yeah. Great. This is great. So a lot of discussions. Okay, so this one, we look at the vehicle capacity and number of customers. So again, we fix the size and the number of charging stations, and the vehicle capacity will vary from 15,000 pounds to 30,000 pounds, but the battery capacity and charging rate are fixed. So obviously, you can see from here very intuitively. When you have a larger vehicle size, the fleet size goes down, right? because of the consolidation, better consolidation of goods, and the VMT goes down. That's very intuitive. And the one interesting thing is, not so interesting, it's also as expected, that when the vehicle size goes up, the energy consumption goes up too, right? Bigger trucks consumes more battery, more energy, right? So, but what that's saying is, well, if you have a smaller size vehicle, maybe the number of fleet size will go up, the VMT will go up, but the energy consumption will go down. So there is a trade-off between the size, the fleet size, and the energy consumption, right? But overall, if you look at the daily cost, so it doesn't really do much affect either way, whether it's increase or decrease. So it's because it's really, when the fleet manager is dispatching the vehicles, so there's also by design the cost is the trade-off between all these things. So if you look at the charging rate, right? So if we vary from 15 kilowatt to all the way to 300 kilowatt, so you see that so first of all, it doesn't change much in terms of the fleet size and the VMT. But it does change the recharging time as expected, right? So if it's higher charging rate, obviously the time will go down, but not so much the energy use. And because of this, then you see the daily operating cost is affected. So, but overall, the charging rate doesn't really change the fleet size, the VMT, or the energy consumption. Okay, so only the in-route charging time that's affected. Okay, so just to recap, so we say, well, based on this study, we found out that there is sort of the right size service area for BETs, and specifically the regional scale seems to be out of bound. And there is an economy of scale for BETs, which is good. And so there are these trade-offs between the fleet size, the charging time, the fleet size, battery capacity, and vehicle capacity, obviously. And both the energy use and the in-route charging time are affected by these factors. And in terms of number, or the customer density, so it's negatively affected, and battery capacity and vehicle capacity is positively affected. Positive means they're both moving in the same direction. So if it goes up, battery capacity goes up, energy consumption goes up, and recharging time goes up, right? And the number of charging stations, as mentioned, in our investigation, does not affect the daily operation. So that may be just because how the network is set up. But if we maybe consider a bigger network, that probably will change the picture here. And the charging rate only affects the route charging time. So it doesn't really affect anything else. Okay. All right. Okay. So I think I still have
15 minutes.
So the second topic. So I'm going to talk about the crowd-shipping. So this project is actually funded by NSF, and we have really this opportunity to work with a crowd-shipping company, a startup company. So one nice thing of that is we actually get the real-world data from this crowd-shipping company to analyze their operation. But a lot of the things I mentioned here is actually based on a hypothetical investigation. So I don't need to mention the e-commerce, and these are some of the existing crowd-shipping delivery services, and so we all use them on a daily basis from one or the other. And so what this crowd-shipping really does is essentially you have a virtual platform typically on a mobile phone, and then the customer sends a request through the mobile phone, and then the platform sends it to the service provider, and then a crowd shipper will deliver the package for you to your doorstep, right? So that's the crowd shipper. So the crowd shippers, they are not the professional drivers, not the, they don't work for any logistics companies. These are just regular people, you and me. So if you have a truck or you have a car, a large car, then you can do the delivery. So that's what the crowd shippers are. And so if you look at the literature, so people typically think that there are pros and cons about crowd shipping. So one thing is, well, crowd shipping tends to be lower cost. Oh, so we thought, so it actually turns out that not necessarily the case. I'll show that later on. And also it increases the vehicle capacity utilization, right? So you have a trunk that's not utilized, you can use that to do the package delivery. And you can use different modes, right? So crowd shippers can be pedestrians, who walk to deliver the packages, can be bicyclists, can be, just automobile drivers, pickup truck drivers, so the flexible modes, right? And so it reduces this parking and loading space for trucks and fast response, right? Because they're flexible. And then also there's some possible disadvantages with crowd shipping. So the issues of this scaling, economy of scale, increasing congestion or environmental impact. And this one, which I think in the business world, this is more the concern. So they consider these crowd shippers are not professional. So a lot of big companies, they don't like to use crowd shippers because there's the company image, right? So you have somebody wearing t-shirts and shorts going into the front door to give a package that's considered very anti-culture of the business world. So oftentimes they have this this perception that the crowd shippers are not professional, right? Obviously they are not professional. So then we did this two hypothetical investigations. So we say, well, we look at the urban micro hub coupled with crowd shipping. And so when then we say, well, we use this delivery truck. So you look at it as like a moving micro hub and coupled with crowd shipping and see, how this different paradigm compared to the current like FedEx and UPS paradigm works, right? So just some motivation why we interested in micro hubs. So in Europe, not so much in the US. So they have already started. This happened in 2018. So they started with this few experiment in Amsterdam. So basically the micro hubs are simply automated parcel station. Okay, so people can deposit and pick up parcels at these stations. So in Amsterdam, they set up these 7 micro hubs. So nobody is actually working at them. Well, very few people working in this micro hubs. And then they have this freight bikes to deliver this parcels throughout the city of Amsterdam. So, and it became quite successful, and now they are actually trying to implement this in other cities in Europe. So, but there's no analytical investigation. So we're interested in seeing, well, okay, so how about we take this micro hub concept, but couple with crowd shipping, because in the Amsterdam project, they don't work with crowd shippers. So they have their own this bike fleet to do the delivery. So essentially we say, well, if we look at this, so the trucks only go visit the micro hubs. They don't do the delivery to the end users or the customers. And let the crowd shippers do the job, the final leg of the last mile to deliver to the customers. So what would happen? I'm gonna skip this one. So it turns out that if that's the case, so this is what currently FedEx is doing. And so most of the cost goes to pay the drivers. So about over 80%, 87% of the cost goes to paying the cost. And then there's other at the center hub operating and so on. And if you look at our scenario, so still most of about 90% of the cost goes to pay the truck driver in this case. the automobile crowd shippers and the bicycle crowd shippers. So we'll consider two types of crowd shippers: automobile crowd shippers and bicycle shippers. In fact, the bicycle shippers has more, consists more percentage-wise. And then we also look at, well, if we increase the number of customers in each zone, so in the service area, okay. So we find out that when the customer density is really low, so this micro hub crowd shipping paradigm doesn't work well. It actually costs more. It's 21% higher. But when the number of customers increases, then you see a large saving in terms of the daily operating cost. So similarly, if we look at the cost per customer or cost per mile basis, so when the customer density is really low, then this orange line represents the micro hub crowd shipping paradigm. So it doesn't work well. So it's more costly than the current delivery paradigm. But when the customer density goes up, and it's performing very well. So in this case, it's even lower cost than the current paradigm. And in terms of the VMT, so the blue bar represents the current delivery paradigm, and this is the micro hub and crowd shipping paradigm. So keep in mind, this is the log scale. So you can see that this, even though it looks like very small reduction, but that actually represents 43% to a 60% reduction in terms of VMT. Okay, so that's a large saving, and then you can also imagine in an urban environment that really translates to less congestion due to the trucks, right? Truck traffic. And in terms of total energy consumption, so it's about a third in any customer number of the customer density case, or the number of customers. So the energy consumption by the micro hub crowd shipping paradigm is about a third of the current paradigm. So this so that what all this point to is, well, great. So this paradigm seems to work very well. And if we look at the moving micro hub case with the trucks, and then the truck will coordinate with the crowd shippers to do deliveries. So the same thing, you look at the total cost, the VMT, so they're all going down. That sounds great. But the question is, why is crowd shipping not as popular as Uber? Right? So that's oftentimes, if you read the New York Times, or, so often say, well, why, we have everybody, how many of you use Uber? So, I mean, probably not so much in Davis, but like in Chicago, so Uber is very popular. But crowd shipping is not catching up. So why is that? Any thoughts? Yes?
Because there are many effective behavior, so you have to have some incentives or penalty to regularize.
Sure, yeah, that's obviously one possible reason. So I have a couple of thoughts on that, so I'll share with you. So one is this fast response versus cost. So we always assume that crowd shipping is actually less costly than regular shipping, right? So it actually turns out that it's not necessarily the case. So we use the startup company's pricing model, and we compare with FedEx. So this line, this is for 5-pound package. This is for 45-pound package. This is for 150-pound package. So this line, the solid line, is the crowd shipping cost, and these are the FedEx shipping. So it's the regular, the ground, the express, and the priority shipping. So what turns out is, if you look at this one, for the very small package, the ground shipping is actually cheaper than the crowd shipping service. Okay, and also in this case, you see this ground shipping cost, at least when the distance is not that long, it's actually cheaper than the crowd shipping. So, but only when, if it's the same, so this Express is same day delivery. Only when it's same day delivery, FedEx is not doing well, okay? So the cross shipping gain this advantage by doing same day delivery. Yes?
And how did you calculate the operation cost for cross shipping?
For cross shipping?
Yeah.
So we consider the same thing, like the driver's cost, the cost for energy and all these things.
So are they all using bikes?
No, so in the previous example, we consider two types of cross shippers. Automobile cross shippers, in that case, they burn energy, right? And then we also consider bicycle shippers, cross shippers. And the model decides how many we're going to hire the automobile cross shippers and how many bicycle cross shippers we're going to use.
And do you know how many of these trips are additional trips? I mean, like motivated by crowd shipping, or because crowd shipping is assumed to be sustainable if it is on the way of already existing trips. However, in many scenarios, it's not like that. So how about in your case?
So in the company we work with, so this actually direct or what I call a dedicated shipping. Not like, okay, you are on your way to work, then you pick up this package. So yeah, so it's totally different from what you were saying. And we don't have the data to show that if they were just like going to work and we pick up like what's additional EMT is going to generate. So we don't have data to show that. Yeah. But I agree with you. So that could create more trips and more EMTs, right, for crowd shippers. Yeah. So so that's the first thought. So the cost is actually not necessarily cheaper for crowd shipping. And the second thought is using this startup company's data, we actually find out there is a discrepancy. There are discrepancies between the sender's demand and the crowd shipper's preference. So unlike the Ubers, the drivers don't really have a lot of preference. So I send a request for a ride and you send a request for a ride. To the drivers, they're all the same, right? So it doesn't matter if it's Jane or Michael. So it doesn't matter. But for crowd shipping, it does matter. So the shippers, these are the bits they post to bid on the packages. So you can see that by distance, so senders tend to want to send smaller package, like shorter distance packages.
Can you explain the axis? We don't see it.
Yeah. So yeah. Sorry about that. So this is the distance. Okay. The distance of the packages to be delivered. So the senders. So these are just the number of requests. So in terms of the size, smaller size, medium size, large size, extra large, and huge size. So you see that the senders prefer to send the package at a shorter distance. So the drivers, the couriers, they prefer to bid on kind of the middle range distance. So you can see that this is where they receive the most bids. And in terms of the package size, so I want you to focus on these two colors. So this is the extra large, and this is the huge size. So senders tend to send the smaller to medium size packages, but the couriers, they like to bid on the larger size packages.
Even though they have regular sedan cars for the most part.
Yeah, interestingly, they may have pickup trucks, but they still prefer the extra large and huge size packages.
They make more money out of it.
Yeah.
That's probably the reason.
For the same amount of time, they make more money if they do bigger packages, right? Because they're generally maybe thinking in terms of trips. Because for them, apparently, your cost is based on trip, not how much time or distance they're in.
That's what we thought, but before I just came out here, my student did a analysis. So we did some machine learning to look at how many bits. So can we predict the bit? How many bits? It turns out the price of the package is not a very important factor, which is very interesting because we thought that maybe it's because of the price, right? Bigger package has a higher price, but it turns out it's not a very important factor. So
do you know what
still.
it is? Huh? Do you know what it is?
So distance, package size, These are important factors. There's one more I forgot what it is. So my student showed me before I came over. But the price is not I think it will be the fifth or the fourth or fifth highest, but not the highest.
Package size wouldn't that be correlated with price because packages are just like more pricey?
Right. Yeah.
More
Sure. Yeah. 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 But it's also the distance too. Yeah.
Okay. So and one question about the diagram. So the sender and courier. Sender are all the requests they're pushing out that these are.
That's regular customers like
Yeah.
you and me. Yeah.
Right, and then the courier is if I accept the request, what are those accepted requests? That's what you plotted there.
No, these are not the accepted requests. These are the bids.
Mm-hmm.
So what happens is in this startup company, what they do is on the platform,
right.
You have the customer sending out the request,
Right.
and then they allow the drivers to bid on those packages. So you say-
Oh, okay.
So they have the minimum price for this delivery, and the drivers typically they will bid a little bit higher than that so that they can get a job, right? So that's this what is showing is the bids received for each package.
So is this like this is a platform that connects just senders to couriers. That's
Yes.
what it is, right?
Mhm.
So
Yes.
senders are wanting to do shorter trips, and then people are bidding for
The middle
medium
size,
and
middle distance.
Sender would be Amazon and all those, right?
No. The senders are just anybody.
Regular people.
Regular people or
okay,
can be
okay.
small business owners and it can be anybody.
So instead of going to USPS.
can be hotel owners or parcel,
Right, yeah, so can be anybody.
grocery stores.
Yeah, whoever signed up for this service.
How the platform sets the prices?
So the price is based, the two primary factors, one is the distance and the size.
Oh, okay. So it's not based on bidding between
You
the
mean the bidding?
senders and couriers?
So that's the minimum price. So the platform sets this minimum price and then the drivers can bid on, based on that, they bid.
They get the highest bid or the second highest bid?
So then the senders will receive this information, then they pick which driver they want.
Oh, they pick, the sender pick.
The sender will
There's a
pick. So it could be based on purely just the price, who has the lowest price, they will choose that. Or it could be based on the rating. If they don't trust this driver, they say, well, I don't want you to.
But the bids are, I'll do it or I'll do it for this price. Whatever.
I'll do it for this price.
So they-
I mean,
they set
for the price they name, but the price will be at least higher than that minimum price. Yeah. Right. So okay, yeah. And then the other one is the delivery time window. So this is whether so the senders prefer the same day delivery. So the package, but the drivers are kind of spread out. They want not just one day, can be many days. So you have this large discrepancies between the senders and the drivers, which is very different from the Uber service. We don't see this kind of discrepancy much in the Uber service.
Where is this startup based?
I'm not supposed to tell.
Because
It's in the U.S.
In the US.
Yes,
okay.
it's in the US.
Uber in the big city.
In the big city.
Okay.
Uber will not do it today or 2 days, right?
Because I think it's depending on location, it's very interesting to see how the mismatch.
Right. So this is definitely in the big city.
I also am interested in the pattern of the demand. How is it? Is it stochastic throughout the day?
So definitely it varies.
So it's not like passenger to have AM, PM.
No, it's not like that. It's
So
not like that.
actually
I
that's
actually
one of
we did
the-
the analysis, but I forgot this, how the
Because
issue is.
you asked that why it's not as successful as Uber passenger. I think one of the reasons is that because it has a stochastic nature,
Mhm.
and many of those couriers are already signed up for other platforms like the passenger, so it's more promising. So
Mm.
sometimes the platforms like don't have really enough supply to meet the demand. So yeah.
It's possible, yeah. But I think this really is a big problem. There's this mismatch of the preferences between the drivers and the senders. So really, so what I think is practically this is the last slide. So I think that like when we are modeling this two-sided market, so currently we don't do much about this one, the driver behavior. So I think this really needs to be incorporated for crowd-shipping service. So for Uber, probably not so much, because drivers they don't know the destination until they accept
It's a
ride.
centralized management. But even in crowd-shipping, we have like those types of services as well. There are different platforms. I think this one is the binding one, but there are different types as well.
Okay, so quickly, I think some of my thoughts about the future logistics. We know that they're already experimenting with drones, robots doing the fulfillment centers. These are talking trucks, right? Connected trucks and 3Ds. Think about this. I think this one will really change the logistics landscape. So you can locally produce or manufacture things rather than shipping. So this is some acknowledgement. And I'm gonna stop here. The references.